So this set of videos on the electron cloud is going to cover from last year what you did in Unit 2 as well as in Unit 3. So we're combining a lot of things into this video or this set of videos on the electron cloud. So if we start off, we want to review with you what electromagnetic radiation is, because electromagnetic radiation is what has allowed us to learn all about the electron cloud. So it is a form of energy transmission in which electric and magnetic fields are propagated as waves through space. Okay, so it's energy that behaves like a wave. It's how energy gets transmitted through space. The sun gives off electromagnetic radiation that warms the earth, that gives us light, and so on and so forth. It is produced, here's the thing that allows us to look at the electrons in the electron cloud. Electromagnetic radiation is produced by moving charged particles, which we know electrons are charged. And so it's typically what we refer to as light, but it is really a wave of energy. Okay, so a wave has certain characteristics about it. It has amplitude, it has wavelength, and it has frequency. So amplitude is the maximum height that it reaches. I'm going to pull up the diagram here. So amplitude is the height of the wave. Wavelength is the distance between consecutive peaks or consecutive troughs, however you want to call it. And then frequency is the number of cycles per second. So if we were to put a line here, the frequency would be how many waves pass that line in a given amount of time, usually in 1 second. So if you think about it, think about the relationship between wavelength and frequency. If the waves are really spread out, if there's a huge wavelength, so if we stretch this wavelength out to here, what's happening to the frequency? The bigger the wavelength gets, the fewer waves are going to pass that given point. So there's an inverse relationship between wavelength and frequency. Notice the units for wavelength and frequency. Wavelength is some sort of distance. That makes absolute sense. Frequency, you're going to hear it in hertz. If you look at your car radio, there might be an HZ when you turn your radio on. When you start to change the FM or AM frequency of the dial, you see hertz. But hertz is really the unit a second to the -1. How many things per second? So cycles per second, waves per second, however you want to think of it. Remember that electromagnetic radiation spans a huge set of waves. Visible light obviously is the one we're most familiar with, but notice it goes from gamma rays on the left here to radio waves on the right. You learned last year that as the wavelength gets bigger, we move from gamma rays. Gamma rays has the smallest wavelength, then we got X-rays, then we got ultraviolet light. Remember, these three are very dangerous because they are very small waves. These guys are less dangerous, including visible light, because they are longer wavelengths. And so the relationship between wavelength and energy is inverse. The more energy something has, the smaller the wavelength's going to be. So these guys have the most energy. These guys have the least amount of energy. Visible light, we typically say that it's between 400 and 700 nanometers. Notice that it kind of goes beyond those two a little bit. We didn't worry about that too much in first year. We just said 400 to 700, but it's in the 300 range to in the 700 range. For visible light. Again, you've seen something like this during first year. Just gives you an idea of as the wavelength gets bigger, the frequency gets smaller, and the energy also gets smaller. Size-wise, you can see how different things are stacking up to the wavelength lengths. All right, let's get into some more information. So all electromagnetic radiation has an amplitude, a wavelength, and a frequency. It also travels at the speed of light in a vacuum. So the speed of light in a vacuum is 3 times 10 to the 8 meters per second. That's a constant that you're going to use in this unit. But keep in mind that that is the speed of light in a vacuum. Light's going to travel a little bit differently, a little bit more slowly if you have it passing through air or water or something like that. It's actually not going to be too noticeable to us, however, that it's not traveling at 3 times 10 to the 8 meters per second. Frequency, wavelength, and velocity have the following mathematical relationships. If you were in honors, you saw these before. If you weren't in honors, this is your first time seeing them. So the speed of light, c is the speed of light, is equal to the wavelength times the frequency. So that is one equation that you want to keep in mind. You multiply wavelength times frequency and you get a constant, the speed of light. Oops, that is supposed to not be there. The other equation that we want to take a look at is the energy versus electromagnetic radiation. And so remember that energy is, or electromagnetic radiation is said to be quantized. It can only come in discrete quantities. Well, we didn't really get into details in first year, but those quantities are integers of Planck's constant, h. I know, again, if you were in honors, you saw this before because we did some calculations. So now we're going to throw energy in there. Energy is equal to Planck's constant times frequency. There's a direct relationship. The more waves you have passing a given point, the higher the energy is. But there's also an inverse relationship between energy and wavelength. As the wavelength gets bigger, the amount of energy gets smaller. Can you see that C equals lambda nu is kind of in this these two versions of the equation? So here's an example. What's the energy in kilojoules of radiation with a frequency of 1.53 times 10 to the 14 hertz? Well, you already see the answer there for you. Be careful about units. Okay, remember that a hertz is per second, so second to the -1. Planck's constant is joules times seconds. So here, hertz and seconds will cancel out, but we're in joules. We need to get to kilojoules. So be careful about your units. That's the one place where people tend to mess up doing these wavelength and energy calculations. All right, so white light, I know you know, is composed of all the visible wavelengths of electromagnetic radiation. If you run white light through a prism, you wind up with a rainbow, just like what happens when the sun shines through droplets that are falling from the sky. You get a rainbow. You can see the individual colors. So what a rainbow is a continuous spectrum. The colors bleed into each other, so you have no empty spaces between the colors. You have all of the reds and the yellows merging to give you various oranges and so forth. So that's what you see when you see white light passing through a spectrum. A discontinuous spectrum, however, is what happens when you pass the light that's emitted from something that doesn't give off pure white light through a spectrum. So most substances don't give off white light. They usually only give off certain wavelengths. And so if you pass that light coming from something through a prism, what you get is something called a line spectrum. It's discontinuous because you see the lines. It's not a continuous spectrum, it's a line spectrum. And this is what happens when you pass the light coming off of an atom through a prism. You see these individual lines, and each element has its own unique set of lines. So if you remember last year, we did a couple lab activities where we played around with colors. So one of them was we did something called a flame test. We put various substances, ionic substances, in a flame to see what would happen with the colors. And so what you wind up with is, for example, lithium gives you red, sodium gives you orange, potassium gives you, that's supposed to be like a lavender color. It looks a little more white than lavender. Copper gives you a bluish greenish color. And so every substance produces a color that is probably not white. If it's white, it's just by chance that you get from exciting the electrons when you put it in a flame. So this is not a chemical reaction going on. This is just causing the electrons to jump around inside the electron cloud, and as a result, energy gets released during some of the transitions. If we were to look at those colors through a prism, what you would see is something called an emission spectrum. So in that last slide, we looked at lithium, sodium, potassium, and copper. Natrium is the name of sodium. That's where Na comes from. Kalium is the Latin name for potassium, which is where the K comes from. So lithium looked red because look at the emission lines. There's an orange one and there's a red one. So it makes sense that overall it should look red. Sodium looked orange. Potassium looked purple. We've got a reddish line here and a purple line here, so you get a little bit of lavender. And then copper gave us a green color because we got yellows and greens in the emission spectrum of copper. Each line that you see corresponds to a particular movement of electrons within the electron cloud. So you have an electron moving from one ring to another. And that's what causes the individual lines to form. There's also something called an absorption spectrum. It's kind of the opposite of an emission spectrum. What you're seeing is the light, not that's emitted, but that's absorbed from an element. So instead of seeing the colored lines being given off by the atom, what you're seeing is the absence of those lines. Notice that the lines are exactly in line with the lines from the emission spectrum. So we've got the Bohr model. Let's review that idea. So remember that we said Bohr's model has rings, and that the electrons can move up and down this by absorbing or releasing energy. In order to go up to a higher ring, energy has to be absorbed. And in order to go down to a lower ring, energy has to be given off. So it's at this point, when the energy is given off, when the electron's returning from a higher energy level to a lower energy level, that it releases that electromagnetic radiation, and we can see that light. So Bohr's electrons, Bohr has claimed that electrons orbit the nucleus in certain allowed energy levels. So the electron can be on the green rings, but that can't be in between. Okay, and so we've talked about these things being quantized energy levels. So certain quantities are what's allowed. If they remain in that circular orbit in these energy levels, then they have a constant amount of energy. However, if they want to move, they have to absorb energy or give up energy in order to get to a new ring. They can't go in between the energy levels, which is why we say that energy levels are quantized. And I'm running out of time, so we're going to get more into the hydrogen atom in the next video.